Good morning friends, I am Vinod Kumar. I am currently pursuing my MTech from NIT Durgapur. So actually today the topic of my interest is strength of materials. Strength of materials. What is strength of materials? Actually, what is strength of material? The strength of material actually deals with the behavior of the materials when subjected to the external load. So it means that it deals with the behavior. Strength of material deals with the behavior of the solid objects when subjected to the external loads. Okay, next here, so actually the study of strength of materials. What does the study of strength of material mean actually? The study of strength of material actually mean when the structural members are subjected to the external loading, what types of stresses are induced. Okay, now actually the study of strength of materials, it means that the study of various methods of calculating the stresses. For example, I will explain briefly the structural members. Now we have different structural members and loading. For example, shaft is one of the structural members. So I have shaft. If the shaft is subjected to the torsion loading, what types of stresses are induced and how we are going to calculate. Similarly, second one, if a bar is there, bar is also one structural member. If the bar is subjected to the tension, what are the stresses induced and how we are going to calculate those stresses. Similarly, the third one is beam. If the beam is subjected to the transverse shear load, if my beam is subjected to the transverse shear load, what are the stresses induced and how we are going to calculate those stresses. Similarly, 4. If my column is subjected to the compression loading, what are the stresses induced and how we are going to calculate those stresses. Similarly, we have pressure vessels. If my pressure vessel is subjected to the internal pressure, what are the stresses are induced and how we are going to calculate the stresses. The study of strength of materials deals with what are the different methods of calculation of stresses that are acting on the different structural members when subjected to the different loading conditions. The strength of material is nothing but the study of the stress, where the calculation of stresses methods. Now, before entering into the actual subject, we will deal with some basics. We will going to discuss some basics. Now, actually, strength of material. What the strength mean? The strength of material, it means that the capacity of a material to withstand the external loading without undergoing any failure. What is the failure criteria for strength of materials? What is the failure actually mean in strength of material? So the strength of material, the metal or any solid object is said to be failed when it exceeds the yield point during its loading. So the failure point is nothing in strength of material is nothing but the yield point. Failure point is nothing but the yield point. So this is the thing. Next we are going to discuss some generalized assumption. Generalized assumptions. So it means what? Generalized assumption. These assumptions are generalized. Generalized means these assumptions are valid throughout the strength of material subjects. So this is the common assumptions that is applicable to every structural member in the strength of materials. So what is the first assumption? The first assumption is homogeneous. It's a common assumption, but the first assumption is homogeneous. The structural member, the metal, the solid object we have taken is assumed to be homogeneous. The homogeneous means the properties. The homogeneous means the material properties like shear modulus, Young's modulus and bulk modulus. All these material properties are constant throughout the object at each and every point at a given direction. Second one, isotropic. The material that we have chosen for stress analysis. nothing but a structured member is assumed to be isotropic. Isotropic means the properties similarly the same. The properties Young's modulus, bulk modulus and elasticity modulus is same in all the directions at a given point. Second thing is static loading. Third thing is static loading. Static loading. The whole strength of materials deals with the static loading. Next important assumption is the failure. In strength of materials, the failure point is considered to be a yield point. The failure point is considered to be a yield point. So this assumptions is of course this assumption is valid for ductile materials. This assumptions is valid for the ductile materials, and we will see the assumption for brittle materials later. Okay. Now these are all the generalized assumptions that is valid throughout the subject. Now we will enter into the subject. Now actually, if you see, I have a rectangular billet. When it's subjected to the external load. So what happens when I apply external tension load to the rectangular billet? What happens? So what happens here is the internal forces will get generated. So these internal forces will tries to oppose the external loading force. These internal forces that is created inside the materials to oppose the external loading per unit area is nothing but the stress. So this is the stress, nothing but the internal resisting force per unit area. Next thing is when you apply the force to this material, the material will tries to elongate. So now the material it tries to elongate. So this is the initial position. Now it has got elongated a little bit. So the deformation that is induced inside in the materials because of external loading is called the strain. This is called the strain. Nothing but the change in length divided by the original length. These are the two, stress and strain are the two important concepts in the strength of materials. Next thing we are going to see is now you have a solid object. Now you have solid object. Now you are interested in how much load it can withstand without any failure. What is the maximum load carrying capacity? What is the maximum load bearing capacity of the material when subjected to the external load? That is your concern now. Now how you are going to calculate it? Now this is the force. So the very first step you have to do is, first of all, you have to know the complete description of the geometry. So complete description of geometry. It means now the solid object I have taken is rectangular in shape. So it is in rectangular in shape. Next important thing is the type of loading you are applying on the object. The type of loading you are applying on the object. These two things are primary things we have to know, and with the help of this type of loading and geometry you can calculate the stresses and strain. That means the stress can be calculated as, stress is nothing but the load per unit area. So here if you concentrate here area, so now here I am assuming that area is constant throughout the loading operation, but actually it is not there, but I am assuming that area is constant. So if you assume the area is constant throughout the operations, it means that you will get the stress strain curve you got based upon this constant area assumption is nothing but the engineering stress strain curve. So this is called engineering stress strain curve. In reality what happens is when you apply the load, the cross section area going to decrease. So then this is called engineering stress, and the true stress is nothing but the load divided by the instantaneous area. This will give the true stress. Okay. Now similarly you can calculate the engineering strain and also you can calculate the true strain from these two data. Now next step is now you have got these stress strain values in your hand. Now if you want to know the load carrying capacity and behavior of the metals, you have to plot the stress strain values pictorially, that means graphically. So the graph of, this is the stress and this is the strain. So now you have this stress and strain values in your hand. Now just plot the curve. The curve will look like this thing. The curve will look like this thing. This is the curve that you got by plotting the stress and strain values when subjected to the loading. So when subjected to the loading. Now here I will divide these graphs into different regions. So this is region 1 and this is region 2, this is region 3, region 4, region 5 and region 6. Okay, now here the region 1 is nothing but the region 1 is stress strain graph is nothing but the proportional limit. It's nothing but the proportional limit. Here proportion between whom? Here the proportion between the stress and strain. So there is a proportion between, there is a directly proportion between the stress and strain. It means that the stress varies strain directly. That means this relationship is valid only in the proportional limit. So this relation actually given by Sir Hooke's. So that's why this is called the Hooke's law. That's why this is called the Hooke's law. The main assumption in Hooke's law here is this relation is valid. This validity is highly important. The relation validity is highly important because you have to know where we have to apply this relation. So validity. What is validity means? It should be uniaxial loading, and also this relationship is valid only up to the proportional limit only. This is about the reason number 1. Now we will see the reason number 2. Now what is the reason number 2? So my reason number 2 is nothing but the elastic limit. The reason number 2 is nothing but the elastic limit. What is elastic limit? At this point, if you just remove the load, the solid object will regain its original shape and position and the dimensions without any distortion. So it will gain its original shape and dimensions without any loss. Next one, reason number 3. The reason number 3 is called the upper yield point. So before that one, what is meant by yield point? So this is yield point. The yield point is an intermediate region between the elastic range and plastic range. That means below the yield point, the region is called elastic range, and after the yield point, it is called the plastic range. Now here you have the material I have taken is mild steel. So mild steel will exhibit two yield points. One is upper yield point and one is lower yield point. Next, if you 3 is upper yield point and region 4 is lower yield point. And now if you see the region, this region is called strain hardening region or work hardening region. Strain hardening region or work hardening region, and the region between the 5 to 6 is nothing but necking region. The region between the 5 to 6 is nothing but the necking region. Now point 5. Now region 5. The region 5 is ultimate. The region 5 is ultimate tensile strength. It means what? This is the strength. This is the maximum strength that the material. This is the maximum stress that the material can hold. This is the maximum strength that the material has when subjected to the static loading. Now point 6. So the region 6 is nothing but the rupture point. This is the failure point of a solid object that you have chosen when subjected to the static loading. This is the final point. This is the at this point the metal will get failed, broken into two pieces. So this is nothing but the rupture point. So now here, what is the use of this stress strain curve? So from the stress strain curve, you can deduce one important. That means you can get one important property. One important property is called the elasticity modulus. So what happens? See here, this is the straight line. The straight line up to the proportional limit. This is the straight line. So this straight line has got some slope. That slope is nothing but the slope. The slope is nothing but the stress divided by the strain. stress divided by strain. So this slope is nothing but is represented by E. It's a constant. E is nothing but the elasticity modulus. Previously we had seen the Hooke's law. That means stress is directly proportional to strain. Now this proportionality can be eliminated with the help of a constant. So stress is equals to E into epsilon. This is the relation given by Sir Hooke. So E is nothing but the elasticity modulus or nothing but the slope of the stress strain curve between the proportional limit and between these two regions. Okay. Now you have learnt about these things. Now one important thing is the strength of materials. The scope of strength of material subject is within the up to the yield point only. They take up to the yield point only. So this is the scope of strength of materials. This is the scope of strength of materials. Because this is nothing but elastic region. This is nothing but the elastic region, and beyond the yield point it's the plastic region. Beyond the yield point it is the plastic region. This is the subject of concern for manufacturing and production technology. That is not the scope of the strength of materials. The scope lies within the elastic region only. So now here we have a brief idea about the stress strain curve. Okay, now we will analyze furthermore. Now the first question is why you have got two different yield points? What is the concept behind the upper yield point and lower yield point? What is the concept behind upper yield point and lower yield point? What is the concept behind getting two different yield points for a mild steel under static loading? So the reason here is you can get the exact reason when you go into the material science. So just simply I will explain the reason. Now if I draw the 2D lattice structure, this is the 2D lattice. Here iron atoms are there, iron atoms are there. This is the 2D lattice structure of the mild steel I had taken. So these atoms are iron atoms. So here the mild steel composed of iron atoms are also carbon. So if you see the size of the carbon is lesser than the iron atom, so it will occupy the interstitial sites. It occupies the interstitial site. Okay, when this metal is subjected to the loading, you have got some dislocations. Assume the metal has some edge dislocations. So this mild steel as consisting of the carbon atoms, the size of the carbon atoms which is lesser than the iron atom, that means which is lesser than the parent atoms, it will try to accommodate in the interstitial sites. Okay, try to accommodate in the interstitial sites. Now if the material has got nitrogen atoms previously, this nitrogen atom will travel and get diffused below the dislocation. So here you will get the atmosphere of the carbon and the nitrogen. So this atmosphere, the atmosphere of carbon and nitrogen atoms in the interstitial site is nothing but a quadral atmosphere. So actually this nitrogen atom and carbon atom will settle below the dislocation only. Why? Because according to the stability principle, they will get, if they settle here, they will feel the stability. So because of stability criterion, they will get settled below the slip plane. Actually this is nothing but an extra half slip plane. Nothing but this extra half slip plane means extra block of atoms. When you apply a load, this extra block of atoms will try to move from one slip plane to another slip plane. Okay, now what happens here is up to the proportional limit load, there is nothing is there. But when you apply the load after the proportional limit, this slip plane will tries to move. But here but because of the quadral atmosphere, due to the carbon and nitrogen atoms present here, it will these atoms will create the stress field. This stress, because of this stress field, it will restrict the movement of this movement of the slip planes for further movement. So because it restricts the movement of the slip plane, so it requires the more load. It requires the more load. It requires the more load for the movement of the slip plane. So that's why, if it requires more load, means the stress increases. So the stress increases. The stress increases because it requires more load for further movement of the slip plane. So stress increases. So once it crosses the quadral atmosphere, there is no restriction here. So its yielding point will decreases. So this yielding point will decrease. This is the reason behind the upper yield point and lower yield point. This upper yield point, lower yield point is due to the presence of the quadral atmosphere because of the carbon and nitrogen atmosphere into the interstitial states. Okay. Next, second thing is, in designing of the metals, which yield point you have to take, whether you have to take upper yield point or whether you have to take lower yield point. In design, you have to take lower yield point. Why not upper yield point? This is the question. So what happens here is, because the upper yield point you will get upper yield point only when the extra half slip planes encounters the quadral atmosphere. Once it crosses the quadral atmosphere, there is no restriction is there. So it is a temporary phenomenon. It is not a permanent phenomenon. So the lower yield point is a permanent phenomenon which you should take into the design consideration. That means your failure point in strength of material is lower yield point, but not upper yield point. Okay. Next analyzation from this stress strain curve is, next thing. Why only you have to plot stress in y-axis and strain in y-axis? Why not interchange? That means why not we can't interchange? That means here you have plot stress in y-axis and strain in x-axis. Why? What is the reason behind this thing? What is the reason? So the reason is, now if you go from mathematical point of view, if you write any function, y is a function of x, it means the x is an independent variable, my y is an independent variable. It means my x-axis is nothing but the x-axis nothing but the independent variable dependent variable in the coordinate system, independent variable in the coordinate system. Similarly, my y-axis is nothing but the dependent variable in the coordinate system. That means you are assuming that strain is an independent parameter and the stress is nothing but the dependent parameter. That means in universal testing mission, you are assuming that the strain is an independent variable, but stress is an dependent variable. That's why you are plotting the stress in y-axis and strain in